So when would strain hardening be useful? Well, if we want to make a material have a higher yield strength, for instance, maybe we want to create a really high-end aerospace part that has a high yield strength so it can endure more stress, and we can run it at faster rotations or speeds. Well, this could be a really useful thing. We just deform it, and now we've raised the yield strength of it. Extremely useful. One reason it could be a serious problem is, let's say we're trying to manufacture something. We're trying to do a process where we cold forge something, we strain it, we die, stamp it, whatever we do, we're straining that material. We've made it inherently harder to deform for our next process. Maybe we need to bend it 15 times before we get it into the shape we want. Well, every time we bend it, it's becoming harder and harder and harder to deform. And even as we do that, we're seeing the material, in addition to becoming stronger, it actually becomes more brittle and it's more likely to crack. So our strain hardening, there's a formula for strain hardening that we can use, where it's defined as the percent cold working, and then we have our initial area, original cross-sectional area, our deformed cross-sectional area over the initial cross-sectional area. What this is telling me is how much of that material has been cold worked, and from that we can figure out from a curve the impacts to our yield strength, hardness, and elongation of failure. So what this graph tells me is, if I know the percent cold worked, right, so I know how much that material has been cold worked, I can figure out from this graph what my new elongation of failure is going to be, my new yield strength, tensile strength, and my new hardness. So here's a good problem for you to work at home and try to figure out the changes in yield strength. So in this case, I have for a 1040 steel, right? So 1040 steel, which would be this one on the graphs, that is cold work 10%. So 10% is going to be here, right? How much does the yield strength increase? So, to do that, you would need to know the initial yield strength, and then you need to know the final yield strength and figure out how much is changed. Okay, so I'll probably post this example worked out for you. I don't want to do it. I want you to actually try to do it on your own. Or maybe that's something we'll talk about in the online office hours that I'll have posted later. We'll figure that out though. Same thing here. Here's another one you can work out on your own. We have for a piece of brass, original cross-sectional area of 10 centimeters squared and a final cross-sectional area of 10 centimeters squared. What percentage of cold working is done? So in this case, you need to use our percent cold working formula and determine the percent cold working, and then figure out from that, use the graph to figure out the new yield strength. Okay, let's talk a little bit about grain boundaries. Grain boundaries are considered defects. So some people have trouble even putting that together, but grain boundaries in a material are considered defects. So grain boundaries are these boundaries of polycrystalline material you see here. So this is a polycrystalline material, and you can see the different orientations of the crystal create these boundary conditions. And at these boundaries, you can clearly see, do the best I can here to show these, but you can see the differences in the grain structure, and these are considered defects. So as you increase the number of grains, you tend to decrease electrical conductivity and thermal conductivity. These grains can provide nucleation sites for corrosion, and they also influence slow permanent deformation. So there's some ways that structure is impacting the material properties. Okay, so let's look at determining grain size. So a lot of times we want to know, well, how many grains do we have in a material? So we want to know the grains over a certain area. So we want to know the number of grains over a certain area. So the reason we'd want to know that is because the yield strength of a material is equal to the initial yield strength plus this ky, this constant, over the square root of the average grain size. Now the question is, what is this formula telling me? As the grain size goes up or down, how is the yield strength affected? This particular value right here, this is something you'd look up in a table, and it's dependent on the material. It doesn't change. So for aluminum, there's a certain constant. For steel, there's another constant. But this value can change. So as the number of grains goes up, what happens to the grain diameter? That's maybe one way to think of it. As you increase the grain size, you actually decrease the number of grains. But as you decrease the grain size, you increase the number of grains. Because the smaller the grain diameter, the more grains you can fit into a certain area. All right, so this D is the average grain size. So the smaller the grains are, the more there are. But even just thinking in terms of this mathematically, you can kind of ignore this square root. It's not necessarily critical to the conceptual thought process that we're going to use here. But as D goes up, it's in the denominator of this particular equation. So as D goes up, what's going to happen? As the average grain size increases, this number, this whole term right here, is going to decrease. Okay, so our yield strength is going to be lower if we add a smaller number to it. Now if I decrease D, if I lower D, that's going to cause this term to go up, and I'm going to increase my yield strength. So if I decrease my grain diameter, I increase the total number of grains, and I increase my yield strength. Okay, so yes, grains definitely matter. The grain size matters. It affects the properties of the material. So if we're talking about ASTM grain size, there's a standard way that ASTM has come up with to measure grain size, and it's the grains per square inch at a magnification of 100x. Now that would be great if we could measure the grains at 100 mag for all materials, but that's not always possible. Sometimes the grains are so small that we can't see them even at 100x, meaning 100 times magnification. So there's some ways we can get around that, and I'm not going to go into deriving how you use this formula to get to this formula. That's not so important to me. But understanding that this formula, this is the ASTM grain size number. This is the number of grains per square inch, and M is the magnification that you're at. Okay, if you know these two things, which is usually what you'd know if you were looking under a microscope, you'd know the magnification you're at because you've set it in the microscope, and then you'd count the number of grains per square inch that you're viewing. So those are how you'd measure them, and then this ASTM grain number is what you would report. So, different steels or aluminums can report an ASTM grain number, and some people who want to purchase certain numbers would be concerned about that. Okay, now how do you count the grains if you're looking at them? And there's a video that's in my courses that's going to explain this in more detail. But the key concept is that a full grain is going to be something you count here, and anything that is touching the side, anything that is not in full view, is considered a half grain. So here's a good practice problem. So you'd want to count all the whole grains. So this would be like 1, 2, 3, and you'd count all the whole grains, and then you need to count these half grains as well. So 1, 2, even this is considered a half grain, so we count that as 3, 4, 5, 6, 7, 8, 9, so on and so forth. And you'd take the amount of full grains, whatever number that ends up being, and then you'd add it to 1/2 times the number of half grains. And that would be your number of grains per inch squared if this is 1 inch here and this is 1 inch here. Okay, here's another opportunity for you to practice. This is a real SEM image here. This is at 1000x. That's the magnification. You can see in real life the grain structure is not always as clearly defined and easy to determine as it may seem in something that's more symbolic like this. So, for instance, where does this grain right here begin and stop? Is this considered a grain? Some of these more nuanced questions, you really need to have an understanding of what material you're looking at and what it is you're seeing in the image. So that's all part of it. And so here's another opportunity for you to practice doing the best you can, since I didn't tell you what material this is. And one thing I'll say, things that you see like this is most likely dust or dirt that's on the image, so you can ignore that in your counting. This would be a 1 grain here. This is going to be a grain. This is going to be a grain. But do not count these things as grains, these little things as grains. And if you see something that, here it's a sort of a tough one, that's a judgment call, whether this is 1 grain here or 2, and whether this connection here is not clearly visible. That's a judgment call. And the reality is those, being off by 4 or 5 grains in something with this many grains is not going to make a significant impact on the STM grain number. Okay, so I'm going to talk a little bit more about this in the video that I'm going to create for the going through my courses. So we're going to hold off on this. And that's it. I hope your weeks are going well and that you're staying safe. Thanks.